Hi everybody, so let's start to talk about these electrons in more detail. We've already mentioned that they live in energy levels, and that's what you see in this picture. The energy levels, remember, are the paths around the nucleus where the electrons orbit. But we need to get a little bit more detailed. You need to know how many energy levels does an atom have, but it's really easy. It just equals whatever period the element is in on the periodic table. In case you forgot, a period means a row. So any element that is in period 3, the electrons occupy 3 energy levels. If an element's in period 7, then it occupies 7 energy levels. And the energy levels are a little bit different. Notice that really close to the nucleus right here, it's much littler, and they get bigger as they go out. The reason that that matters is because littler means they have less energy. So the energy levels closest to the nucleus have less energy, and as you go farther and farther out, they get more and more and more energy because they get bigger. Okay, when we put them all together in a diagram like this, that's what the Bohr model is. That shows the electrons in the correct energy level. So that's what this picture is at the top. It's just called a Bohr model. That's really important because it helps us identify the valence electrons. Okay, valence electrons are like the special ones that they live in the outside energy level. So that would be here. So any electrons that are traveling around this very outside path are called the valence electrons. We need to be able to calculate how many valence electrons an element has. Also super easy. It's just based on its group. A group is a column, just in case you forgot. So all of the elements in group 1 have 1 valence electrons traveling around in that outer valence shell. Okay. The rest of the electrons are what we call the core. So those are the electrons inside the valence shell. They're still there, they're zooming around, they're just not quite as interesting, but they're the other electrons, the core ones. The last thing that we can do is we can make a Lewis dot diagram, which is a picture that shows the valence electrons with the element symbol. So we're representing those valence electrons in a picture. So let's do some examples of that. So grab your periodic table. Carbon has a total of 6 electrons because it equals the atomic number. So I can write that. The energy levels equals the period. So carbon is in period 2, which means it has 2 energy levels where its electrons live. The valence electrons equal the group. Now carbon is in group 14, and so what we do is we chop the 1 off, and it has 4 valence electrons. So we're going to turn those into a Lewis dot diagram like this. You put the symbol of the element, and then I want you to imagine that this element is in a box. Okay, we're going to put 1 dot on every side of the box. So 1 on the top, 1 on this side, 1 on the bottom, and 1 over here. Now, we don't really draw the box, so it looks like that. Okay. Notice that when I did that, I went around in a circle. Okay. This full octet column we will come back to in a little while, so don't stress about it quite yet. Let's talk about hydrogen next. So hydrogen is in group 1. So find that. Its atomic number is 1, so that's the number of electrons. The energy levels equals the period. It's in the first period, which means that it has 1 energy level for its lonely little electron to zoom around. The group number tells us the valence electron. It only has 1 electron anyway, so that is also its valence electron. And then I can draw its Lewis dot diagram like this with 1 dot. It doesn't matter where you put that 1 dot. You could put it on that side. If you really want to put it on the other side, it doesn't matter. There's only 1, okay? Magnesium, the atomic number is 12. That's the number of electrons. Magnesium is in period 3, so it has 3 energy levels for its electrons to live in. It's in group number 2, so it has 2 valence electrons. So I'm going to draw that like this. Here's magnesium. I'm going to start on the top again. I'm going to put 1 dot there and then 1 on this side, and that's it. Okay. Oxygen. Oxygen has an atomic number of 8. It is in period number 2, so it occupies 2 energy levels. It's in group number 16. It does not have 16 valence electrons. We chop the 1 off. It really only has 6 valence electrons. So when I put that on my Lewis dot diagram, it will look like this. I'm just going to start on the top. So 1, 2, 3, 4. Now that every side of my box has 1 electron, now I can go back and double up. So I can do 5, 6. And so I get a pair of electrons here and a pair of electrons here. There's nowhere else to put them, so that's okay. All right, let's talk about neon next. Neon has an atomic number of 10. It is in period number 2, so those 10 electrons live in 2 energy levels. It's in group 18, and so I'm going to chop the 1 off. That means it has 8 valence electrons altogether. So here's how that looks. Again, if you want to put this in a box to help yourself think about it, that's okay. So I'm going to do 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to erase that box. That's the Lewis dot diagram for neon, okay? All right, helium's a weirdo. Put a big star right here. Every rule that we make has to have an exception. Sorry. All right. Helium has an atomic number of 2 for 2 electrons. It's in period number 1, so those 2 electrons zoom around in 1 energy level. Now, it's in group 18, but the 18 doesn't make sense. It can't possibly have 8 valence electrons because it only has 2 altogether. So this is an exception. Those 2 electrons that it has are also the valence electrons. It can't have 8. It only has 2 at all, okay? That means when we draw its Lewis dot diagram, we do it a little bit differently. Normally, we would put those 2 dots separate. That's the rule that I just told you. Sorry, that's the rule that we're breaking. Because it's helium and it only has 2 electrons altogether, we draw them together like that, okay? That's the only time you'll do it. So every rule has an exception. Sorry, helium is the weirdo in this case. All right, let's try a couple more examples. Potassium is K, 19 electrons altogether. It is found in period number 4, so those 19 electrons live in 4 energy levels. It is in group number 1, so only 1 of those electrons is in the valence shell. That means when I draw it, I just need to put 1 dot for it, okay? Let's keep going. Now we have nitrogen. Nitrogen has an atomic number of 7. It is in period number 2, so those 7 electrons live in 2 energy levels. It's in group number 15, which means that 5 of those electrons are valence electrons. So I need to put 5 dots around. So I'm going to do 1, 2, 3, 4. Now that every side has a dot, I can double up. So I'm going to put number 5 up there. Okay. Argon. Argon is another noble gas over in group 18. Its atomic number is also 18. Okay. It's found in the 3rd row, the 3rd period. So there are 3 energy levels holding those 18 electrons. Then I know that because it's group 18, I chop off the 1. It has 8 valence electrons. So I'm going to do AR, and I'm going to do 1, 2, 3, 4, 5, 6, 7. There are my 8 electrons, okay? All right, let's try a couple more. Aluminum. It's atomic number 13. It's found in period number 3, so those 13 electrons live in 3 energy levels. It is in group 13, which means if I chop off the 1, there are 3 valence electrons. So I'm going to put 3 dots around it, okay? Last one is fluorine. Fluorine has 9 electrons. It's in period 2, so those 9 electrons live in 2 energy levels. Because it's in group 17, I know that 7 of the electrons are the valence electrons. So I'm going to put an F with 7 dots around. So 1, 2, 3, 4, 5, 6, 7. There we go. All right, so the nice thing is a lot of these are really predictable patterns. We know that the energy level is based on the period that the element is in, okay? So all of the elements in period 1 have electrons in 1 energy level. In period 2, the electrons live in 2 energy levels. In period 3, they live in 3 energy levels, and so on down. So if you can identify the period, you know the number of energy levels. Valence electrons are kind of the opposite. The valence electrons equals the group. Remember, we also call that family. Okay, it's the column. So everything in group 1 has 1 valence electron. Everything in group 2 has 2 valence electrons. We're skipping the middle on purpose, and that's okay. Everything in group 13 has 3 valence electrons. So over here, one of the things you're going to want to remember is chop off the 1 from the group number. Okay, that means group 14 does not have 14 valence electrons, it has 4. The elements in group 15 have 5. 16 has 6. Everything in group 17 has 7 valence electrons. And group 18, except for helium, our weirdo, they all have 8 valence electrons. We skipped the middle because they're also kind of weirdos. Remember, we call that section the transition metals. They do not follow a predictable pattern. So there's no magical way to know how many valence electrons they have, which means we're not going to ask that to you. That's not a fair question. There's no way for you to know. Okay, so you focus on where we wrote this pattern. That's what you need to tell us the valence electrons for. Okay, now the noble gases, group 18 over here, these are pretty special. Having 8 valence electrons constitutes what we call a full octet. This is a hugely important rule for atoms, okay? The octet rule, just like octopus has 8 legs, octet means 8. So the octet rule says that all atoms want to be stable, just like the noble gases are, because they have 8 valence electrons in their outer shell. Okay? For me, my dream is to have a couple $1 million in the bank. For an atom, their dream is to have 8 valence electrons in their outer shell. That makes them really, really stable. That's what they want to be. So neon is an example, right? Neon has 10 electrons altogether. Here's 2 in energy level number 1. And then there's 2, 4, 6, 8. So altogether it has 8 valence electrons. This is every atom's dream. This is what they all want, okay? Having 8 electrons on that outer shell is the best thing that an atom could have, okay? We could also represent that with the Lewis structure for neon with those 8 dots. Every atom wants to have 8 dots, but they don't always get it, okay? Now, our one exception to that rule, again, is helium. So helium is the kind of weird exception. It is still a noble gas. So for some elements, they do want to be like helium. Okay, it doesn't have 8 valence electrons though. Remember, it only has 2 valence electrons. And that's okay, right? So for some elements, if they're nearby helium on the periodic table, then they want to look like helium with just those 2 valence electrons. So let's flip back a page and let's identify whether these elements have a full octet or not. Okay, so carbon, I see 4 dots. It has 4 valence electrons. It does not have a full octet. It would like it, but doesn't have it. Helium only has 1 valence electron. That's not an octet. Okay. Magnesium has 2 valence electrons, 2 dots, not a full octet. Oxygen only has 6. It's close, but that's not 8. So no, there's not a full octet there. Look at neon though. There it is. Neon. Yes. This one has the full octet. This one is what all of the other atoms want to look like. These are the cool kids. Everybody wants to be like them. Okay. Neon and helium are both noble gases. So helium also has a full octet, but it's kind of like an exception. It has an octet even though it only has 2 electrons. That still makes its valence shell full. Okay, so everybody wants to be like neon, everybody wants to be like helium, everybody wants to be like those noble gases with their full octet. None of these have full octets, they don't have enough. Oh, argon, there's another noble gas. It has 8 dots, it has 8 valence electrons, so yes, this one is another full octet. Atoms want to look like argon. Poor aluminum does not though. Fluorine only has 7 dots. It's close, but still not a full octet. So there you have it, octet rule. Good job, guys.